looking for alternative ways to power embedded sensor nodes. The idea being that if you run a embedded sensor node off a battery and periodically have to change the batteries, it's not really an embedded system. You're periodically having to attend to it. And some of the potential uses that we have, those sensor nodes might be in hazardous locations, maybe something like a big bridge structure where it's hard to get to the node and you don't want to put a person needlessly in danger just to change a battery. We actually bring the energy to the sensor node with a remote controlled vehicle. There's nothing magical about the helicopter per se. That's just the robotic device that we've tried it with first. QA and one of our postdocs, Kevin Farrenhold, has also done the exact same thing with just a ground-based robot. In fact, one you could just buy at a hobby store to drive around, but it has a power source and battery on board. It flies within the vicinity of the sensor node and actually has to get fairly close. It transmits radio frequency energy to a receiving antenna connected to the sensor node, charges up a capacitor on the node, and when a certain voltage is reached in the capacitor, there's enough energy there for the sensor node to take its reading and broadcast it back to a receiver on the helicopter, and then the helicopter can go on to the next node and take other readings. Our first field demonstration last August of this system, and now we're working on a next generation of system that initially we just took individual sensor readings, if you will, a scalar quantity. What we're trying to get to now is to be able to measure an entire time series. So I'll maybe take a 1024 point time series of sensor readings, and that then allows us to do other kind of data processing and a lot of the stuff we're looking at it to be able to assess damage in structures. So that allows us to use a lot of different data interrogation techniques if we have a time series as opposed to an individual reading. That's a big step forward in the amount of data we have to store, acquire, transmit, and so forth. That's a huge step up for us. And the reality is, if we do it in beyond just a proof of concept demonstration, it'll probably be some hybrid system where we make use of more traditional energy harvesting approaches like a solar array, coupled with this information retrieval system that's facilitated by the UAV or the robotic device. The life of these systems, the electronics will be out of date before the system would not work anymore. Because the electronics are a fairly rapidly evolving part of the technology. And so we're building these sensor nodes right now, and I think even in the time that you've been building the sensor nodes the last couple of years, there's been changes in the electronic components that are available, things like that, to make them more efficient. Different types of integrated circuits that are on them that can allow for different type of sensing and data interrogation. So I think with these systems, the issue is going to be the electronics are going to be out of date before the system will not be able to work anymore. Energy harvesting to power sensors for structural health monitoring then is one particular area where that might help. The structural health monitoring is the application that facilitates the integration of the technology. If we want to use this energy harvesting to actually power the sensors and then convert the sensor data into information about the condition of the system, that means we have to integrate the hardware and the data interrogation software. We can apply those sensing systems to a wide variety of problems. So a couple of ones are trying to look at how we can harvest the energy to have essentially a zero power sensor system that could be used like for perimeter monitoring. If you're worried about intrusion into a particular area, you want to monitor foot traffic, and you want to allow the vibrations caused by that foot traffic to actually power the sensor that's trying to sense that foot traffic. Most of the material right now is a piezoelectric material that we can either use as a sensor or an actuator. And so when we use it as an actuator, we refer to that as active sensing. And a lot of times if we tailor the waveform that we excite the structure with the actuator, we can enhance the ability to detect damage. In a sense, trying to tune the energy harvesting device, like if it's harvesting mechanical energy, to the dynamics of the system. Yeah, so we have actually, some of the summer school students that we've had a couple of years ago did studies on could you mount the energy harvesting device on a surrogate structure that's then attached to your real structure, and have the dynamics of that surrogate structure tuned such that you maximize the energy available from the host structure. So yeah, and we were actually able to see increases in performance of the energy harvesting capability of the piezoelectric materials through tuning that structure to the dynamics of the host. What we hope to be is actually deploying it on real-world systems, not just doing it in a proof-of-concept mode. It would be 10 years is a long time. We should be at that level, and that time, if we were to keep up the level of effort we have going to date for that time, we should be at a point where we've transferred this to real-world applications. If you focus just on the energy harvesting aspect of it, I think that is pretty close to being able to be done right now. But again, for an owner of a structure to want to do this, it's more than just harvesting energy to run the sensor. Can they actually get useful information out of that sensor system? There's a lot of different components to this technology development, and our university systems are not so as developed to train a more multidisciplinary engineer right now, and that's what we've been trying to do with a program here at the University of California at San Diego. And I think, you know, we're just now getting it off the ground, and we have gotten some people through, at least at the master's level, and it's just starting to get people through at the PhD. And my assessment is time will tell, is the bottom line about how successful it is. The first few people coming through, it's going to be they're going to have much more of an issue of what do they want to do, rather than are they going to have something to do. Because of that multidisciplinary background, they can fit in a lot of different places. So the example being our student David, who developed the helicopter, did all the work on the helicopter and some of the sensors. Right now, you know, biomedical companies, you know, want to work with him on other types of robotic devices, in vivo surgery devices. And he has a skill set now to allow him to adapt to that type of activity. I would also make the claim that the technology leaders of the future, the policymakers, are going to have to be much more multidisciplinary than somebody like me who was educated 30 years ago. Okay? And we need to have that pipeline of young people coming through right now for the future. You know, you don't have just a great big breakthrough. It's very slow progress sustained over long periods of time, and then you slowly get there. And when I was in graduate school, I worked out at Edwards Air Force Base, and I heard a great talk by one of the Air Force guys there, and he was talking about the efficiency of the rocket motors that they were using on the missiles there. And he just showed this chart of where they just made all these small, like 1% increases, but over 10 years, they had a 30% increase in the performance of the rocket engine, just by doing all these little small things over time. But anybody would say a 30% increase in performance, that's a big step forward. But there was no one thing that was the step function to get there. It was just a lot of little things and a sustained effort over a long period of time.